In the previous video, we did this simple problem using the blue method, best linear unbiased estimator, where the problem was to get two measurements, Z1 and Z2, of this state X. And we know the first and second, oops, we know the first and second order statistics of these errors, of these measurement errors. And they're all also uncorrelated from each other. We imposed linearity, we imposed unbiasedness, and I kind of zipped through the algebra here. But when I take the expectations of these V terms, because of the problem setup, those are zero. So that helps simplify some of the algebra. And then best was minimum mean square error. Again, it showed up here, these B's, because their means are zero, that helped. And because they're uncorrelated, that helped too. It wasn't just algebra. It was part of the problem statement that helped us simplify all that. I don't want to go through all this again, but we came up with an answer where the answer was the weighted sum of the two measurements. And we could also calculate the variance in the error of our estimate. Now, this video, I want to look at the same problem recursively. And now we could have more than two measurements. We might have a whole bunch of measurements. And the way we want to do it is after each measurement, we update our estimate and we update the variance in the error of our estimate. Ka-chunk, ka-chunk, ka-chunk. So those are the two things. This X hat sub I is the estimate of X after the ith measurement. And this P it's the variance because the expected value is zero. So the mean square is the same as the variance. These are the two things we carry along. Estimate and the variance in the error of that estimate. If we only had one measurement, due to linearity, you'd have this. Our estimate is just some scalar multiple of the measurement. What's the expected value of that? Expected value of our estimate is the expected value of Z times that C1. And the Z was this, but the expected value of V is zero, so it's just C1 times the expected value of X. And unbiased requires that this expectation equals that expectation, which means this C1 is just 1, which was a long way to get to what you would have thought in the first place. That with only one measurement, your estimate is the measurement. And by similar type of approach, the variance, the error of that guy is just the variance of the measurement error of the variance of the measurement error. That all makes sense. So that's after one. After two, we just went through that problem, so we know how to come up with that answer. And it was this. But now look, because P sub 1 is the same as this sigma sub 1 squared. So we can replace these sigma sub 1 squareds with P1. Now look at this. All we carry along is our previous estimate and this P1. Everything else comes from what we actually get at that second measurement, which is the measurement itself and its variance of its error. Similarly, for our update of the variance after the second one, it would be this when we replace all these sigma sub 1s with the P1. And again, we don't even have to carry along. We're not carrying along all the information. It's just the information we get at that second time step. And once we had a way to know how to find it with two, now we can do it recursively, where the two things we combine is all the previous stuff we had. Now at X3, the estimate of X3 is the estimate of X2 and the P2 we had after 2. And then all the new stuff, and then the new measure. So you have this general relationship for any sequence. And convince yourself with a little bit of algebra that this line is the same as that line. Because this is going to be our way of thinking about it, summarized over here. Our new estimate at this time step is the estimate we had the previous time step plus this correction term. This part, this X hat is our, you could call it our estimate of what we expected to measure. So this little difference here is the difference between what we measured and what we expected to measure. And this part here is called the gain. And look at how this, let's look at the two extremes. If this gain is 0, then the updated estimate is just the old estimate. I didn't use the new measurement at all. And if this gain is 1, then I get this x hat of k minus 1 minus x hat of k minus 1, and all I'm left with is the z sub k. It says my new estimate is just the measurement of time. So that's what the gain does. It tells you how much to weight those two things, your previous estimate and what you just measured. And everything on this left side, the estimate and the variance of the error of our estimate, is all based on things we had previously, P's and the previous estimate, and the new things with that new measure, the measurement itself and the variance of the error of that estimate, that measurement. Anyway, this is the approach we're going to take for the Kalman filter, and so that will be the next video.